I'm going to try this again, this time maybe recording the entire screen. All right, first up, scalars have only magnitude. That tells how big they are, or how much speed they have, or how long something took. Direction doesn't matter. Distance, speed, and time are just a few of our scalar quantities. The other piece to that could include direction. If a scalar quantity includes direction, then that makes the quantity become a vector. This reminds me of speed, which equals a distance over a time. This would be our average speed. So we could take our total distance and the time that it took to travel that distance versus the average velocity, which is a vector quantity. So velocity, magnitude, and direction matter. We use our displacement, final position minus the initial position, over time to find that average velocity. All of our velocity quantities are listed in the parentheses there: displacement, velocity, acceleration, force, weight, torque. We haven't talked about torque yet. Momentum, impulse. That's what we are going to cover on the midterm exam. Everything else comes after the break. Big thing with vectors, direction matters. If you are changing directions, then you need to include the opposite sign for your quantity. Instantaneous values represent quantities at a specific moment, while average values describe quantities over a time interval. There's our average velocity and there's our time interval. You could get even more specific to find our velocity as a function of time by taking the position derivative with respect to time. That would give you your instantaneous velocity. Acceleration tells us how much an object's speed or direction changes in 1 second. Emphasis on the direction because acceleration is a change in velocity over time. If I change the direction of my velocity, I'm still changing my velocity. If I change the speed, I'm changing my velocity. Either one of those would count. It's how much your speed changes every second. When an object speeds up, the acceleration is in the same direction of motion and velocity. For example, our motion diagrams. If we have these dots, remember these motion diagrams are like strobe lights, they're flashes, and we see the object with equal time intervals between here, call that delta t, and all the way over here, delta t. We can tell that we've covered a greater distance in the same amount of time here, so we're faster in the second gap here. And then even faster in the third gap. So that means we're speeding up. In this case, if our velocity is to the right, our acceleration is also to the right. If the dots are becoming closer together, then our velocity could be to the right, and in this case our acceleration would be to the left. Whatever direction your velocity is the direction the object is moving. When the object slows down, acceleration's in the opposite direction. There's our relevant equations already talked about. Motion diagrams, those are those dots that show position and velocity. We also have position time graphs that we're going to talk about and velocity versus time graphs that we'll talk about. And of course, not to be forgotten, the acceleration versus time graphs. You should know some general things about these graphs. If we take a position versus time graph and we have a horizontal line, that means we have zero velocity because the slope of a position versus time graph is velocity. No slope, no velocity. If we have a sloped line, that indicates a constant velocity. So we want a constant slope there because the slope of a position versus time graph is velocity. At all points, my slope remains the same, so my velocity is constant. I could then go on a velocity versus time graph and plot that constant. In this case, we have a constant positive, so that's what that would look like on our velocity versus time graph. We can go even further to our acceleration versus time graph. There's no slope on this velocity versus time graph, and the slope of velocity versus time gives you acceleration. That means there is 0 acceleration for this situation. When we go into more difficult graphs, position versus time graph that maybe does something like this, and we need to turn that into a velocity versus time graph, then we're going to use the phrase starts blank, ends blank. For our position versus time, we start at 0. We'll just say it starts positive and is constant. So we start with a constant positive. Then we have 0 velocity. And then we have negative constant velocity. So we'll have negative constant velocity. And then that stays for a long time. And then all of a sudden it does whatever I drew there. I guess 0 velocity again. So we start blank, goes blank. Let's do another one. This time, a little bit more realistic data. That's going to make more use of the starts blank, goes blank phrase. All right, fine. I'll just erase everything and make it nice and new. Happy? Say we have a graph like that, whenever we have a curve on a position versus time graph, that indicates there is some acceleration happening there, which means there's a change in our velocity. So for this graph, I'm going to just say that this is a constant line. So I start with my constant positive velocity again. Then I start constant positive and I go to 0. So start constant positive, done, and then go to 0. Now I can do this slash line. Next, I start at 0 and I go negative. Starting at 0 and then I go negative. Those time intervals should line up. So we were 0 velocity for some time, and then I went negative velocity, and then I start negative and I end at 0, starting negative, ending at 0, and then starting at 0, going positive. So then I would start at 0 and go positive. You can do the same practice. Starts on the velocity versus time graph, the slope starts 0. So our acceleration would be starting 0, starts 0, and then a constant negative, then we're back to 0, then we have a constant negative, and so on. Position versus time graphs. The slope of a position versus time graph is velocity. The slope of a velocity versus time graph is acceleration. The way I like to think about this is x VA, and as we go down, we have to take the slope. To go backwards, we have to take the area under the curve. Area under the curve to go back up. To determine instantaneous speed from a curve position time graph, take the slope of a tangent line. Let's say we wanted to find exactly at 3 seconds what our velocity is. We're going to, at 3 seconds, draw a tangent line and then take the slope of that tangent line, and in that one exact spot where the tangent line touches our curve, that is where our slope is, whatever this is. For position versus time graphs, our detector, the motion detector that we used, starts at 0. Our motion detector, remember, this was a tool that we've used that sends off this sound that clicks, and then it registers them back, and however long it takes for the clicks to come back, that helps determine the speed of an object or the distance it is as it moves away. So that detector can only work with positive position versus time graphs. If anything is behind it, the detector doesn't know. To determine how far the detector how far from the detector an object is, look at the vertical axis of your position versus time graph. So if we come up to 5 meters, that means we're 5 meters away from our detector. To determine which way the object is moving, we need to look at whether the velocity versus time graph is positive or negative. If we're in the positive area, our velocity is positive. So we're moving in the positive direction. The direction of your velocity is the direction of your object's motion. Even though my velocity is approaching 0, we're getting slower and slower, we're still in the positive direction. We're just approaching 0, approaching a stop sign, but still moving forward. Then we turn around. Whenever we pass through the x-axis on a velocity versus time graph, that indicates a directional change. Now we're in the negative direction. In this case, my velocity is speeding up in the negative direction. That can throw you for a little bit if you're not used to it. By now, though, hopefully we're good with that. Kinematics equations are 3 kinematic equations. We can use these if and only if we have a constant force or constant acceleration. We need to identify initial conditions, list them out. So we can list out all of our givens. We have our x, we have our v naught, we have our t, and we need to find acceleration. We can do that. As long as we have 3 of those things, we can use those equations and solve for the missing one. But only if our acceleration is constant. Should be able to look at an equation and determine the units for it by now. So if we wanted an equation and we wanted to know what a Newton was, I'm going to take my net force and set that equal to ma. So Newton, mass is measured in kilograms, acceleration is measured in meters per second every second. So that's what a Newton is. That kind of thing, regardless of the equation. We can also use dimensional analysis to make sure the equations are used correctly. It's kind of a way to check yourself, especially on free response questions. On my classes, midterms, there are no free response questions. So, problem for another day. Free fall. An object is in free fall if gravity is the only force acting on it. An object can be in free fall even if it is moving up. If I throw an object directly up, it's going to be slowing down. Well, when I think about the free body diagram acting on that, after it leaves my hand, the only force acting on it is the weight force. So, this object is in free fall, even though it's going up and not falling, and even though it's slowing down and not speeding up. We're assuming g equals 10 meters per second squared downwards. Be sure to let the grader know if you are doing something weird, like taking down to be positive or left to be positive. You can just draw a little coordinate system like that to indicate. Normally, we use right to be positive and up to be positive, but sometimes it's useful to do it opposite. And if we have down to be positive, then we're just going to plug in 10 meters per second squared into our equation wherever there's a g, and we're good. If we take down to be negative, then we better include that negative in front of the 10 meters per second squared. Otherwise, we're going to get some wrong answer. Objects dropped from rest have 0 initial velocity. That dropped and initial velocity equals 0, those are synonyms. When you read dropped, initial velocity is 0, while objects thrown upwards will have some initial velocity. We can use these relevant equations, which are the same exact kinematic equations. We already know that acceleration is going to be constant as long as there is no air resistance. How do we know there's no air resistance? We're going to ignore air resistance until the problem tells us there's air resistance. Whenever we have a vector acting at some angle, we need to resolve the vector into its components to make a 90-degree right triangle. Our horizontal component has to act independently of our vertical component. If we have 0 drag force or air resistance, then we'll have 0 horizontal acceleration. Meanwhile, the vertical acceleration will be g unless we're way out into space. If we have an initial velocity, say a cannonball launched from a cannon at some angle theta to the ground, that cannonball has an initial velocity in the x component, which we're going to use v naught cosine theta, and an initial velocity in the y component, v naught sine theta. We use the right triangle, and it makes our life easier. We know how to deal with having a hypotenuse and an angle to get the opposite side, or having hypotenuse and an angle to get the adjacent side. Adjacent means touching, so if your side of the triangle is touching the angle, then that's your adjacent side. Opposite's the other one. There are those right there. Those are probably useful to have memorized. Vectors can be added or subtracted graphically. Tip to tail is a method. So if I have vector A that points up and to the right, and then I have vector B that points left, and I wanted to add those two graphically, what I'm going to do is I'm going to, I'm going to move that whole vector. I'm going to move vector B's tail to the tip of vector A. Then my resultant, or the result that I get when I add these two, is going to be up and to the left. That's how I would add it graphically. If I were subtracting, let's use numbers because those are comfortable. 5 minus 2 equals 3. That is the same thing as 5 plus a negative 2 equals still 3. So what we do when we subtract is we add the opposite. We're going to do the same thing. If I subtract vector A from vector B, which was over here, the opposite of vector B is going to be the anti-parallel vector. So it's going to be pointed to the right. So now I'm going to do the tip to tail thing, and then my resultant vector is going to be in this direction. This is A minus B, and this is A plus B. Resultant vectors can combine 2 or more vectors. This process works if we have 10 vectors, 3 vectors. You won't see too many vectors because it takes a little while. Should also be able to add vectors mathematically. And we do that, again, we're making a right triangle. So if I take my x component, let's say my vx, and my y component, and I wanted to find my velocity, I'm going to do vx squared plus vy squared. Pythagorean theorem equals v naught squared. A squared plus b squared equals c squared. That's all this says. Your resultant vector in the x direction equals your vector A in the x direction plus your vector B in the x direction. Vector y, same thing. The magnitude and direction of the resultant vector are given by this. This is just resultant, resultant in the x direction, resultant in the y direction. This is if we have multiples, and we add them and we get that. To find the direction that our resultant vector is pointing, we're going to use this directional formula. No need to memorize the direction formula because you already know it. You know it as tan theta equals opposite over hypotenuse. Over adjacent. And if I'm just solving for my angle, I need to take arctan from each side. And I get theta equals opposite, arctan opposite over adjacent. Or y over x. AP Physics C. We deal with three-dimensional motion. We can still add vectors mathematically. To do that, though, we're going to use our unit vectors I hat, j hat, and k hat. We don't do it too often because it doesn't pop up too often. At least it hasn't popped up too often for the x, y, and z components. So the I hat is the same thing as x. Just keep that in mind. And the j hat is the same thing as y, and the k hat is the same thing as z. I, j, k, alphabetical order. X, y, z, alphabetical order. No need to ever get them mixed up. If we have vector A, who has coordinates of 3i hat, 5j hat, and 2k hat, and we have vector B, which has coordinates 2i hat, 5j hat, 3k hat. To add these two vectors together, we're just going to do 3 plus 2 is going to be 5i hat, 10j hat, and 5k hat. That's our resultant vector. That's it. I think it's a bit easier than the algebraic version. Then, of course, we can combine multiple vectors in our Pythagorean theorem. X, y, and z, or I hat, j hat, k hat. And all of those vectors squared. For relative velocity problems, relative velocity depends on the motion of both objects. Think about walking on the moving sidewalks leading into the airport. And how fast do people look like they're going as they walk on the non-moving ground? For all objects in the same frame of reference, velocity is 0. I think about things in the car. When you're staring down at your phone, that phone to you inside the car does not appear to be accelerating, speeding up, or slowing down. Instead, it's got a velocity of 0 relative to you. To somebody who's standing on the side of the road and looking at that cell phone pass by, that person's going to say that phone is accelerating or that phone is moving. To figure out how fast an object appears to be to somebody else, we can take our apparent velocity, which is what we're looking for, and take the velocity of the object minus the velocity of the frame. Earlier today, there were a lot of questions on this, so we did an example, and we said a person on the ground watching somebody float down the river. And if the person floating down the river was moving this way with a velocity of 10 meters per second, and our person on the ground was moving in the opposite direction of 2 meters per second, how fast would the person on the boat look to the person on the shore? To do that, we're going to take V apparent. The object we care about, the object we're looking at, is the one on the river. So we're going to say right is positive, so we do 10 minus 2. Sorry, I skipped a step there. 10 minus negative 2 equals whatever. Subtracting a positive, subtracting a negative plus a positive. So it appears like this guy is moving 12 meters per second to the right. So it appears like they're moving faster than they actually are. What if we wanted to see how fast the person appeared to be moving relative to the person on the raft on the water? Now we're going to take the person's velocity as the object's velocity, so negative 2, minus our frame of reference, which is 10, and we're going to end up with a negative 12 meters per second. That negative tells us it's in the negative direction, the opposite direction. Projectile, motion. Projectiles follow a parabolic path. There's two main projectile types that we are going to be working with. The first is a horizontally launched projectile, and the second is where we're launched at some height and then come back perhaps at that same height. And the two trajectories look like that. Either way, the projectiles follow a parabolic path, which means they have symmetry. We're going to take advantage of that symmetry to make our problem solving actually solvable. We should be able to analyze horizontal and vertical components separately, just like we talked about with vectors. Velocity is a vector, so we need to treat it like a vector and treat the x components separate from the y components. When you see the phrase maximum height or altitude, that's just talking about displacement in the y direction. The one quantity that's the same for the x and y directions is going to be time. For the horizontally launched projectiles, we have no initial vertical velocity. So our v naught y here is going to be equal to 0. And that's because we're launched at an angle of 0. So whatever our initial velocity is times sine of 0, we're going to get 0. That means all of our initial velocity is our initial velocity in the x. If we needed to find how far away an object would go through the air, we're going to use x equals vxt plus 1/2 at squared. If there is no mention of air resistance, then there is no air resistance. That means there's no acceleration in the x direction, so all of that goes away, and what we're left with is x equals vx times t. Maybe we have that, we're looking for that, but we don't know t. In that case, we're going to use time in the vertical direction. We'll hopefully know our height or altitude, and that y equals v naught y times t plus 1/2 gt squared. No initial velocity in the beginning, so all of that goes away, and our equation simplifies to 1/2 gt squared. We can solve for time here and get t equals square root 2 y over g. And then whatever time we get here, we can substitute back in there, and hopefully we're good. The big thing is when we're listing out the information given to us in the problem, keep your x and y stuff separately. So that way you remember to treat them separately. If we have no acceleration in the x, then 0. If our acceleration in the y equals 10, great. If we know what x is, 32 meters, and we know our height is 10 meters, keep these two things completely separate. V naught x equals v naught cosine theta. V naught y equals v naught y, v naught sine theta. Because velocity is a vector. For our second type, our parabolic motion, again we have symmetry. So that means if we cut it in half, whatever happens on the first half equals exactly what happens on the second half. That could lead to a wrong answer if you're solving for time. Because let's say we need to find the time it takes, or the time this object is in the air, the time the punt is in the air, the hang time. Well, as the ball is traveling, and we say, oh, at the very top, I know my velocity in the y direction equals 0, and my velocity in the x direction equals v naught x. Then I solve for time up at the top. That time is only half of the time. We need to double it, because that's the total time it was in the air. So if there is no air resistance, then we have this velocity in the x. And because there's no acceleration, that magnitude of the velocity in the x is not going to change, even at the top. So just because we have no vertical velocity, that does not mean we don't have any velocity. In the y direction, we're going to start with a really big y upward, and then it's going to slowly decrease because the acceleration's in the opposite direction until our velocity in the y equals 0. On the way down, we're going to see the opposite, where we are speeding up. There's no vertical velocity at the top of the trajectory, but there is horizontal and vertical acceleration. Oh yeah, gravity doesn't shut off at the top. Don't forget that. G is still going to equal 10 meters per second squared at the very top. What's the acceleration at the top? 10 meters per second squared. Half the parabola is half the time. There's all of these equations there. I would not spend time memorizing those. They're just there for you in case you wanted. So if we have to create an experiment here, common types of material found in the lab are going to be useful. We did talk about the motion detector, and that's fine. You might see that as a choice on your multiple choice questions that involve lab design. However, I think you're probably going to see more basic rudimentary equipment. So meter stick stopwatch to find velocity, rather than having a smart cart, because not all schools are going to have access to a smart cart. So we have done it both ways. We've done the high tech and we've done the low tech early in the year with those constant velocity cars. Think back to them. We should be able to validate experimental data and make predictions. So if we were looking at a y versus t graph, that is probably going to be something like that. Nope. Something like that. There we go. How do I know that? Because I know from our last equation, y equals 1/2 gt squared. 1/2 is constant, g is a constant, so we get y versus t squared. What that means is y equals mx plus b. If I wanted my slope to calculate g, then on the x-axis I should have t squared. On my y-axis I should have y. So if I were to plot a y versus t squared graph, now I'm going to get a constant linear graph, because this is my straight line equation. This process is called linearizing your data. Use kinematic equations for comparison. If we'll do y equals 1/2 gt squared. We'll do the other one. X equals v naught times t. If we increased the initial velocity for an object by 4 times, how much farther would it go? The way we would do this is I would say 4. T is going to be the same in either situation, so I'm just going to call that 1. So I have 4 times v naught. That's the same thing as taking my initial equation and multiplying the right side by 4. If I do that, I need to multiply my left side by 4. So I can say my horizontal displacement would increase by 4 times as much. Important skill. Our calculus equations are all here. Kind of talked about them. Whenever you see slope, that's derivative. Whenever you see area under the curve, that's an integral. A force is a vector quantity that describes an interaction between 2 objects or an object and its environment. Common types of forces: gravitational force, normal force, tension force, frictional force, and applied force. Applied force happens only when we have a hand. Also, we have spring force, which is a force that a spring exerts when it is deformed. The net force is the vector sum of all forces acting on an object. Net force equals ma. We like to say net force equals stuff that makes it go minus stuff holding it back equals ma. That way our direction is usually taken care of there. Just don't forget to set it equal to ma, and if we're at a constant velocity, acceleration equals 0. Newton's first law of motion tells us that if we're moving at a constant velocity, that means the net force acting has to equal 0. Can't be any acceleration because acceleration is the change in velocity. If our velocity is not changing, we have no net force. This is the state of equilibrium. That means all forces are balanced in the x direction and in the y direction, or in the I hat, j hat, k hat direction. Inertia is the property of matter that resists changes in motion. It's proportional to mass. The more massive an object is, the less likely it is going to want to move. Push a refrigerator. A refrigerator's got a lot of mass. That means it has a lot of inertia, a lot of resistance to start or stop moving. Terminal velocity is when your acceleration equals 0, so your maximum velocity for a falling object. Terminal velocity happens when we have our weight force down and our drag force up. And those two equal each other. 0 acceleration, terminal velocity. We're going to talk more about that drag force in just a little bit. Oh, and we also have the buoyant force. The buoyant force is just the upward force acting on an object. So if we have a ball submerged in water, we're going to have a buoyant force, and we're going to have a weight force. If the object is just floating at some height, then we know the net force acting here should be equal. Acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass, as seen in Newton's second law. Acceleration occurs in the direction of the net force. So whatever direction is your net force, that's the direction of your acceleration. When there's an equation that's a fraction, the numerator can be plotted on the y-axis and the denominator can be plotted on the x-axis. What quantities should be graphed in order to get a straight line whose slope is equal to a? Well, a equals sigma f over m. So if I plot sigma f as my rise and m as my run, I'm going to end up with a straight line graph whose slope I can use to calculate my acceleration. Remember, whenever you have a graph, the first thing you should do is look at your axes and think, okay, what relationship do I know that relates these two variables? Even if it's like, I know kind of a relationship, mass and velocity. Okay, maybe it's momentum, or maybe it's a curved graph and it needs to be linearized and it represents kinetic energy. Think about those types of things. If Newton's third law of motion, if object A exerts a force on object B exerts a force. I don't know if I copied and pasted this or messed up typing. Probably copied and pasted because I don't use this phrasing. Same magnitude and type and opposite direction. Same magnitude and type. So if I am standing on the ground and I exert this weight force down on me, I have to have a second object to see this. But if I consider the forces acting on the earth in this situation, that's the downward. Now if I consider the forces acting on me, that is the upward force. The normal force is not a force pair in this situation. Instead, it's the normal force would be a normal force because I would be exerting a normal force down and the earth would be exerting a normal force up. So there's that. But also, the earth is exerting a gravitational force on me, and I am also exerting a gravitational force on the earth. So when I jump, the earth comes with me. But because the earth is so massive, we cannot observe the acceleration. So remember that there has to be two objects for a force pair to be seen. A force pair is two forces, same magnitude, same type. Can't be the normal force and the weight force. Has to be normal force and normal force. And in the opposite direction. We should be able to draw and analyze free body diagrams. Free body diagrams represent all forces acting on an object as vectors. So the length of the vector signifies the magnitude of the force to create a free body diagram. Identify the object of interest. You will see a dot or you will see a square. If you start drawing, I always recommend start with the easy one, the weight force, because I know the weight force always points towards the center of the Earth. So the weight force and whatever else, Ft. Draw all forces on the object, labeling each force. The arrows should start from the dot, or maybe you'll have a box, either way. And then, most importantly, label those forces. If you don't label your forces, you're out of luck. You're not going to have fun solving this problem, and you're not going to have fun seeing the score that you get. These are free points. You should gather these free points. We draw a free body diagram whenever we recognize a force problem. And things to recognize force problem are if any force is mentioned, like a buoyant force or a frictional force or a weight force. These are all forces, the F word. So that means we should start with drawing a free body diagram. Next, draw a second free body diagram with your components, because if it's an FRQ, don't draw your components on your free body diagram. That's going to be scored. Second step for forces problem. Second step, second law. The net force equals the stuff that makes it go minus the stuff holding it back equals ma. Once we've drawn the forces and we've labeled them, make sure we go back and double check your labels. I promise you there are a lot of people that, oops, I forgot to label my free body diagram. Don't let that person be you. Each arrow should be pointing away from the dot or box. The length of the arrow should be proportional to the magnitude. Resolve the forces into components if necessary, but on a separate free body diagram than the one that's being scored. If it's multiple choice, it doesn't matter. Skip 1A and go straight to 1B. The normal force is normal or perpendicular to a surface. Scales are going to give you the reading of the normal force. A good example of that is in an elevator. If you were standing on a scale and the elevator is moving upwards and our acceleration is moving upwards, this tells me that my net acceleration acting on me is upwards. So I have my weight force in the down direction, and then I have my normal force in the up direction. Because those are the only two forces acting on me, my normal force has to be bigger if my net acceleration is in the up direction. If my normal force is bigger, that scale is going to read have a reading that's larger than my weight if I were just standing on the side of a sidewalk, weighing myself. If the acceleration is going down, if your net acceleration is going down, so that means velocity up, acceleration down, you're going up but slowing down. Or if your velocity is down and your acceleration is down, you're going down and speeding up. If that's the case, your net acceleration is down, that means your weight force has to be larger. So you are going to feel smaller than you would if you were on a sidewalk weighing yourself. The magnitude of the normal force tells you how heavy you feel. Smaller normal force, you feel lighter. Mass in an elevator feels heavier when the net force is up, and lighter when the net force is down. An ideal pulley has no mass and no friction, so it only changes direction. An ideal string is massless and does not stretch. A massive string means it does have mass, and it might stretch depending on what the problem tells you. For the inclined plane free body diagrams, we're going to start with the weight force pointing down. The easy one, right? Weight force down into the center of the Earth. Next, the normal force is perpendicular to the ramp. Now, to complete this, we should consider the components. So I'm going to continue my normal force into the ramp with a dotted line, and then I'm going to connect the dotted line to my weight force. Whatever angle that ramp was at is going to be this angle right here. That's how we draw the triangle. So that makes this mg sine theta, and that will make this mg cosine theta. The angle between the weight force and the continuation of the normal force is going to be the same angle as our inclined plane was at the very beginning. Then from there you can draw and label all the other forces. If you got tension going up the ramp, and you've got friction going down the ramp, because friction opposes the direction of sliding. So if we're sliding up the ramp, then friction would oppose. Now that we have all of our forces drawn and labeled, we can do our net force equation, but we have to do it twice. Just like we would do if we had x and y, we're going to have parallel and perpendicular. In the perpendicular direction, Fn and mg cancel each other out. So we can say Fn minus mg cosine theta, I said mg, I'm sorry, I meant mg cosine theta, equals 0. So Fn equals mg cosine theta. In the parallel direction, the stuff that makes it go in this situation is my tension force minus the stuff holding it back, which I have two things. Yes, I have friction force, but I also have this mg sine theta that might be overlooked. Be careful and don't forget that. That mg sine theta, that's the stuff that makes it go down the ramp. If there wasn't a tension force, the reason anything slides down the ramp is that small little piece of gravity. If you were asked what causes the object to slide down the ramp and you said gravity, that would be wrong. It's a component of the weight force. The normal force on an inclined plane is not mg. It's going to be Fn equals mg cosine theta for reasons that I just went over. Then we apply net force in every direction. Onto gravitational force and weight. Weight is the gravitational force acting on the object. The Earth is the agent. You are the object. So the Earth is exerting a force on you. Weight depends on the mass of the object and the local gravitational field strength. Our local gravitational field strength is little g, 10 meters per second squared. Little g just means near the Earth's surface. There's a relevant equation. Frictional forces. Friction always opposes sliding, or attempted sliding, or imaginary sliding between surfaces. Opposes sliding. So if I have a box on a flat plane and I've got a tension going this way, the box is sliding to the right. So friction is going to be pointing to the left because friction opposes sliding. If there is some attempted sliding, let's say the box is resting on the ramp, we would have to say, okay, mg sine theta is attempting to get the box to slide down the ramp, but there's just not enough to move it down the ramp. There's too much friction to move it down the ramp. So what direction is friction going to be going here? Friction's going to be going up the ramp because the box would slide down if it were allowed. Imaginary sliding, this is sometimes kind of hard. So if you imagine walking on ice, if there's no friction, my foot would slide backwards, but so if this were a normal situation, when we're on a sidewalk, now my frictional force is pointing forwards. We have two types of friction. We have static friction, and that prevents motion. Your static frictional force is less than or equal to mu s times Fn. It's less than or equal to until it reaches its maximum value. So our maximum static frictional force is equal to mu Fn. Anything else is less than, because the static frictional force has to be overcome before we get the object sliding, and we can deal with kinetic friction. Remember what friction is? It's these tiny little ridges between two surfaces. The coefficient of friction only depends on what the two surfaces are made of, not how big they are or what they look like. It's what they are made of. So these tiny ridges between these two surfaces have to become unlocked, and it takes a lot of force to unlock those ridges that are interconnected with each other. But once it's unlocked, now we can slide relative to each surface. So we would deal with kinetic friction. Kinetic friction acts during motion, and that is just mu k times Fn. Mu k will always be less than mu s. Static friction that helps motion is called traction. We see this in shoes and tires. Static friction must be overcome before kinetic friction is in play. It's always easier to keep an object sliding than it is to start it sliding. A rough surface indicates there is friction, while smooth surface indicates friction is negligible. Little trig fun for you. Sine theta over cosine theta equals tan theta. The reason why this matters is because if we have a box that's moving at a constant velocity, to make this quick, we'll just say the constant velocity is 0. That means the stuff that makes it go parallel to the ramp is going to be mg sine theta minus our frictional force equals 0. So our frictional force equals mg sine theta. If we were asked to find mu s times mg cosine theta, remember mg cosine theta is our normal force, equals mg sine theta, mg goes away, and I'll divide by cosine theta, and I get mu s equals sine theta over cosine theta, or just tan theta. This works as long as we're moving at a constant velocity, because the net force equals 0. Tension is the pulling of force transmitted through a string, rope, or cable. Tension will be uniform throughout an ideal massless string. If we are dealing with a non-ideal string, then that string has some length. And if you take different points on that string and analyze the tension, here the tension is going to be the least, while up here our tension is going to be greatest, because the tension is pulling up while the weight force is pulling down. And as we go further up the string, we're getting more and more mass that we have to deal with, or the string has to deal with. If you do see mass on a string, think forces first, unless it's a pendulum like this. So if we've got a pendulum, I might ask you to think about conservation of energy there, because we'll have a height and we'll have a maximum velocity. You know what? Let me go off script here and consider this pendulum. If I needed to find this change in height right here, because let's say I was working with conservation of gravitational potential energy, the full length of the string is L. All of that is L. Well, as the pendulum slides up, L does not change, so it's still L. If I needed to find this change in height, that means I'm going to take my full length and subtract out that piece of my right triangle. Of course, I would need to know this angle there, which I'm probably given. And now I can solve for this. So this yellow side of the triangle is going to equal L cosine theta. So what is my change in height? It's the full length, L, minus this little piece of the triangle, L cosine theta. Sometimes you may see this rewritten as L times 1 minus cosine theta. Uniform circular motion, it's there for you, but we have not covered it, so I'm not going to cover it. Problem solving with forces. Again, once you realize it's a force problem, if we have mass interacting with strings, springs, ramps, pulleys, elevators, friction, any of that, that indicates a force problem for me. We're going to draw a free body diagram with components, and then stuff that makes it go minus stuff holding it back equals ma for the x-axis and the y-axis, or the parallel axis and the perpendicular axis. Resistive forces are forces that resist. They slow objects down because they act in the opposite direction of motion. You may be given F equals negative kV. And in this case, let's take K to just be some constant of proportionality. Constant. Doesn't matter, just called K. If we were talking about drag forces, that would be your drag coefficient. You don't need to know what that's called. You don't need to memorize F equals negative kV. Just talking here. So you may be given this equation as a drag or resistive force. Remember that F equals F. So we can take that equation that you were given, let's say it's negative BV instead of KV. We can set negative BV equal to MA if that's the only force that's acting on it. If it's not the only force, maybe it's mg, the stuff that makes it go, minus bv equals ma, and we can solve for acceleration. This is how you deal with air resistance. So maybe negative kv equals mg. If that's the case, if this happens or if this happens, because this sometimes will show up as squared, there's the drag force has two equations. I will use B. Drag force equals BV squared. This is for smaller objects. This is for bigger objects. You don't need to know that. You don't need to care. Just know that either one of those is just a drag force. You're going to treat it like a force and stick it into the stuff that makes it go minus stuff holding it back equals MA equation. When this drag force equals your weight force, that means you have a net force of 0. That means you're no longer accelerating. This is terminal velocity. In calculus, you may come across a differential equation or be asked to create a differential equation. That's just an equation with a calculus term in it. In this case, let's take negative BV and set it equal to m dv dt, because that's what acceleration is equal to, dv dt. From here, to solve this differential equation, you're going to get the like terms on one side, so get all of your v's together. And then you're going to integrate both sides. So if you're trying to solve for v, you're going to integrate both sides. There's going to be natural log involved. So if you're not good with that stuff yet, don't fear. You'll get there, and this will be easy for you. But a common answer for this would be Euler's number to the negative bt over m. That's what your answer is going to kind of look like. Acceleration for an outward machine can quickly be solved by treating the system as a whole rather than dealing with tension. If we're only asked for acceleration, let's not find tension. Let's just skip it. Let's say little m and big M. So we're going to say in the system, the stuff that makes it go is big mg minus the stuff holding it back is little mg. That little mg existing is the reason why we're not in free fall here. So that equals ma. And that m is going to be the total mass for the system. So we divide by m1 plus, well, what did I say? Little m and big M. And that would give me my acceleration. Work, energy, and power. Work is the transfer of energy through a force applied over a displacement. Work is the energy transfer of energy, so the change in energy through a force applied for some displacement. The area under a curve, if we're graphing two quantities and they're being multiplied, then we're looking at the area under the curve. So the area under the curve for force versus displacement will give us either our change in energy or the amount of work done. Work is only done if the force has a component along the displacement. To account for this, we're going to take FD cosine theta. That theta is the angle between the force doing work and the direction of displacement. Because of this work energy theorem here, I like to think of work as the bridge between energy and forces. So we've talked about identifying force problems, strings, springs, friction, all that stuff. Well, if we need to talk about energy, along with all of those things, the work energy theorem puts them together nicely. Positive work adds energy to a system. We'll have positive work done on a system if the angle between the two is acute. And negative work happens when energy is removed from the system, usually through heat and sound, friction, or during a collision. And that happens when this angle between force and displacement is obtuse. Work is a scalar quantity, but it can be positive or negative. We get positive work when we add energy to a system, and negative work when we take energy out of a system. Retarding forces like friction or drag are responsible for dissipating energy.